Right, hello everyone. Spencer Suter. I've been at JLR for 35 years now. I do a lot of astronomy and astrophotography, which is embedded in this sort of next talk, so it'll be something different anyway for you. But I'd like to talk about symbiosis. So as engineers, electronics engineering and all that sort of stuff, we need to think about the bigger picture really of what we're here to do on this planet. So it's going to go big, and then we're going to go very small, talking about AVs and sort of sensor sets in AV. So there's a lot of slides. I'll talk quick, and hopefully you can keep up. Anyway, so symbiosis, space, planet, humanity, our experiences on that planet, and then the life cycle of the stuff that we use. We get everything from the periodic table, and it needs to go back into the periodic table. But to get that periodic table in the first place of all the elements, many things had to happen in space back from the Big Bang. And I think we lose that sight of that realistic sort of view that actually it's quite a privilege to have all the tool set that we've got. And if you think of what happened to allow us to have what we need to make things, electronics and all that sort of stuff, there's a couple of cycles of suns had to collide and all that sort of stuff. So the periodic table, as it is that we know, literally it's all coded, colour-coded, so neutron stars had to merge, cosmic radiation, it's all rare stuff. You know, it's a perfect sequence as well to get what we've got. So everything we take, we should always keep out and then, know where everything is almost. That's when you're going to get pure circularity. But the abundant element in the universe is hydrogen. So that might give an indication of where the fuel source should be. Obviously, there's a load of chemistry, and how do you keep the smallest thing in the universe in a bag to fuel cars and fuel homes and stuff? It's a constant challenge. So that's sort of really important to think about, is where does the stuff come from that we use? It is rare. And if you go into global warming, it was first, so the FFT guy, Joseph Fourier, he sort of postulated that the Earth should be 30 degrees cooler based on its position of Earth to the Sun. And then over time it was sort of confirmed. Eunice Foot actually found it. A fantastic scientist that discovered it in her garage, effectively, that CO2 plus water was the real cause. And then it was sort of confirmed in 1969 when they started looking at Venus with the runaway planet. So what's the Sun doing? So this is where it goes, like, the universe to the periodic table to the Sun. So the Sun over time's got its cycles. That painting in the middle there is from 16 something or other, where the River Thames froze over because we had a bit of a mini ice age. And climate naysayers sort of just thought that the Sun was causing the temperature of the Earth, which on the chart there, I would point the chart, you'd say, yeah, that's true. But in about 1980, those two started to diverge. So the Sun was giving out less energy, and the Earth was sort of starting to warm up, which is, the root cause of sort of the climate change phenomena that we've got. So where are we today? So on the left, we've got the sea temperatures. So in 2023, the sea temperature across the planet went really, really hot, due to a couple of things. El Nino kicked in, as we all know. That's sort of the warm cycle of the perturbation that's within the sea. But also there was the Tonga volcano. So a sort of tectonic event happened where it just put up loads of vapour in the atmosphere. That's going to take about 8 years, the climatologists think, to wash out. And the net effect is the sea's cooking at the moment, which is why it's been raining forever, it seems like, in the UK, because the sea's about 4 degrees warmer, and it's just on simmer, effectively. Global temperatures around the world, it's sort of right on the peak on the right side there. So it's starting to come down now slightly. We're only as hot as last year, so it's getting back to new territory. So did anyone see the aurora on the 10th of May? Yeah? So a few people saw it, but that had a real effect on technology. So this is the Sun doing its thing, and it's had a coronal mass ejection, effectively, a mild one in relative terms, but the amount of technology and sensors that we've got now in technology, farming, they were severely hit due to a solar event that you can't predict. You think they're going to be in the 11-year cycle, roughly, but within a 3-year window every 11 years, you could have one of these moments where literally all the farming equipment in the US, which is already autonomous, by the way, or most of it is, GPS signals were off. Everything was to the left by 2 meters or to the right. And a few were reported to go around in circles, but whether they were or not, I don't know. But it was ionic scintillation. Effectively, the solar wind from the sun was compressing the atmosphere on that side of the planet, on the sunny side. So then GPS signals, the timing's wrong. So unless you send out the error, the offset to correct the error, which you don't know until it's there, why will that put onto road passenger vehicles, which will use GPS and all the subsequent systems? And on the other side of the planet, when the solar wind is pushing that way, it bulges the atmosphere, and then all the low orbit sort of satellites that Elon's putting up, quite a few of those have been stressed over the last few months. He did lose 38 actually on one deploy because the atmosphere bulged out and they re-entered. They're in low orbit, but they re-entered the atmosphere because it got pushed away. So these things happen throughout time, sort of every 80 years or so, we have a big event. So the more reliance on space technology, the more vulnerable some of the stuff is. So we need to consider how to protect against that with backup systems and all that sort of stuff. So there's a bigger solar cycle, the Milankovitch, which is sort of the Ice Age one. But with the levels of CO2 that we've got at the moment, it's going to be not a problem in a bad way. But effectively, it's the wobble and eccentricity of the planet with the geometry of the sun. And then solar wind, when the sun's pushing out loads, it reduces cosmic radiation, so it's sort of a perfect balance where we are. So we're quite rare in the universe to be able to be in existence, which I think we sort of forget about. So yeah, symbiosis again, really. The status of the planet in terms of climate change, sort of 6 out of the 9 metrics are over limits. It's all in the press, everybody sort of knows about it, but until you see all the data in one place, it doesn't really get the magnitude that it should have. But ozone, we are making progress on that as a humanity, the civilization, if you like, but it takes a long time. So 1987, the Montreal Agreement removed CFCs effectively from fridges and aerosols. It's taken 20 years to have an actual effect on the petri dish called the Earth and our environment. So things do take time. So climate change is not going to go away very quickly, but we need to keep faith and keep going at it. Biodiversity, who can remember 1976? Yeah? So that's always reported in the UK as being one of the hottest years out, and nothing else is ever good since. It's not as hot since, but top image there is 76, bottom is 23. It's no explanation really, it's just chalk and cheese. The reason why 76 was so dramatic, it was a dry winter, so we'd already going into June with dry soil, so everywhere looked parched. I remember having water bowsers at the bottom of the road to get water and all that sort of stuff. Loads of ladybirds as well, anyway. But the net effect for that was the UK lost 25% of its beech trees. Significant effect on the biodiversity sort of umbrella that we could home in the UK. So 23, 24, where we are now, it's still really hot in reality. But that data comes from a little woods by Monmouth in Wales, 100-acre woods. It's just a scientific study, really. So how do you get nature to be part of industry and be part of the boardroom? So there's a wonderful lady called Gretchen Daly. She started some time ago now to value nature as a cost. So trees, for example, many billions. All the top 50 OEMs are at the top part there, so trees have got more value, effectively, on the planet than all the OEMs put together for automotive. But trees are going to get more stock value when you consider where tarmac comes from. So when oil's not being pulled up out of the ground, tarmac will be likely to be replaced by tree sap. So lots of research in Sweden for that. So the stock value of trees are going to go up as a thing. And all the other sort of natural things there you can see. That's the only way you can balance that sort of stuff. And the ONS in the UK, they actually use this sort of data to show what our biodiversity sort of value is. But at the moment with HS2 and all the other building work, we're actually net negative at the moment because we're digging up the ground. So farming puts a lot of CO2 back in just because you plough effectively. So this is where the astrophotography comes in. So the image top is noctilucent clouds. It's full of methane. effectively. It's radar reflective as well. Some reports of that are coming in. I never used to see them when I was a child. I've been doing astronomy for years. But over the last few years, you can see them every summer, effectively. But it's part of the climate process. They're clouds that are 80 kilometres up, right at the level of the mesosphere and the thermosphere, where it's sort of really cold and really hot, just that transition. And the bottom chart there, you can see the rise of methane due to industrialisation. Effectively, when they port oil out, a lot of methane escapes and that sort of thing. It's part of the industrial process. So we never used to see those. It might cause issues with radar, with technology going forward, but I don't think it's a good sign, and the science is still being investigated onto those. And then lithium batteries, it's environmentally expensive, so once we've got it out, there's lots of programs within JLR research, and they research everywhere how to recycle black matter from batteries effectively. So once we've got it out, we should never put it back into the ground, honestly. It should be just circular. So this room, electronic stuff, there's mountains and mountains full of gold and other rare materials that are just yet to be harvested. But if you go and have a look at how that's harvested, it's really quite an acidic and lots of chemical processes, so it's net bad in itself. So consider where we should put two ECUs together or whatever like that, to start combining to use less of this material. But in terms of circularity, where it's sort of the next stage really of sort of evolution on this planet really, is that we should be starting to refuse things. So this is like a common table effectively from Cambridge University. So refusing product is probably the most circular to do. Actually, I'm not going to do that. I'm going to do something completely different. But the rethink is the one where we should probably go to, which leads to the shared AV. So this is the story getting to autonomous vehicles. So shared AV would be a solution where to use and stress the products and mass that we've got on the planet already. Most companies, by the way, are sort of operating at the 8 and 9. Literature just be legal to get net zero. That's just a compliance thing. It doesn't really say what you're going to do with it. And whether it's good or not. So people should be really thinking about how to do things slightly differently. So autonomous vehicles, classic picture on the right, 1956, I think, somewhere around that era. It's in all the AV books, effectively. So playing Scrabble, looking backwards in a nice, cool dome. I think that vehicle tracks wires in the road. And then there's a more modern version on the left. So this is where motion sickness comes in. So all the AV things that you see, concept vehicles, facing backwards, hugely challenging. So motion sickness is so my PhD was in motion sickness, so you'll get a bit of that now. So it's where you've got an error between your vestibular system, which is the channels in your inner ear, and what you see. So when there's an error there, so you can feel things and you can't see it, or you can see things and you can't feel it. That's when your body says, what's going on here? It's a bit of a problem. And you start to go through this, you feel tired, you get a headache, you go hot, and it will lead to nausea and vomit if you don't get off the bus, effectively. It's generally 0.2 hertz, so 1 cycle every 5 seconds, really, really slow. It's not typical motion of a vehicle, so that's quite a different thing. Confounding factors, age, gender, ethnicity, but most importantly, experience. So 13-year-old females, generally the most sick. But part of the solution to motion sickness is the experience, the habituation. Basically make it an interpolation of motion that you store in your brain rather than extrapolation. Longitudinal direction is worse, braking, acceleration, then it's lateral. Vertical we're okay at effectively, but yaw, not good either. So that's sort of the mechanics of motion sickness. In terms of systems engineering, classic systems V at the bottom, so you'd have the chassis, which is the dynamics part of the equation, and then you'd have body describing the visual side, how much of the outside world can you see. At the middle lecture, you've got the customer experience layer, but then if you go on the upper side of the, the V on the top, that's all the systems we are as people. So the idea is to take the data layer from the systems V in engineering and actually predict the output of the human. So spring stiffness, how does that change motion sickness? So we've done models now effectively to do all of that. I think it's a really good way of expanding systems engineering to include the human more. Because when you think AI and tuning models and everything else, you really need to get to these, how does it affect somebody that's purchased that? I've got 20 seconds apparently. So anyway, there you go, systems engineering. So evolution, motion sickness came in with fish, effectively, 550 million years ago, because they were the first creatures that had got a vestibular system, the one channel, effectively, a thing called the hagfish, slime fish. Then everything to the right, from fish, amphibians, reptiles, birds, mammals, they all get motion sick. We all get motion sick. The only people that don't get motion sick are the profoundly deaf or with vestibular dysfunction. So everyone does it, but there's like a bravado. I don't get sick, but, give me an office chair and a bucket, we'll be all right, we'll get you sick. So, interestingly, crabs also get sick. They get air sick. So the Norwegian fisheries, they stop people pulling out the crabs, the king crabs now, out of the sea, because they're, it's animal cruelty, really. So, yeah. But at the bottom there, you can see lots of mass extinctions. So we talk about that. Happy subject. But the one to pay attention to is the one at 365 million years ago, the Devonian one. And that was a mass extinction due to the dominance of one species, and that was plants. So when plants went from the sea, effectively, across the ground, they basically sucked all the oxygen up, and that sort of cut back 75% of the richness and biodiversity of the planet. So we need to consider that when we think, well, actually, what are humans doing at the moment? So we're in the Holocene at the moment. We're rocking about 1,000 times the extinction rate than the normal baseline. Normal evolution forces extinction, because that's the whole process, but it's on the negative side at the moment. So it's just something to consider a little bit. So humans, 99.975% of the time, the Earth had no knowledge of us being in existence. But in the last 0.025%, we've generated boats from Indonesia, floors, Mesopotamia, that's where the wheel was invented, loads of farming, which is effectively Syria, Turkey, northern Iraq, Iran, around there, between the Euphrates and the Tigris River. It's quite fertile land. So that's where civilization sort of started from. So if you take the wheel, on the image on the top left there, and then 1600s, pictures of, I was looking for when do people face backwards in cars and transport. So sliding carts had wheels in 4,000 years ago, evidence that people were facing backwards in carts, then in stagecoaches, then on trains, then autonomous vehicles. And then over to the rest of this presentation with the keynotes is how do you get all of the sensor sets to make all of that safe. So the image on the bottom right there, that is a solid-state LiDAR that effectively got in my PhD about 6 years ago, so I'm sure it's smaller now. But in terms of where next, trust, I think, is a huge thing. AVs are going to be driven by AI effectively, which is just maths. But obviously, there's a human perception that could be bad. We need to sort of address that and bring the humanity along with us on that journey. Loads of requirements. Let's think about how we're going to get our navigation from clearly a challenging environment in low orbit. Circularity. People only ever talk about the negatives, really, of AI and quantum in terms of cybersecurity threat. But there's loads of positives with quantum and loads of positives with AI. How to engineer faster. And I think that's one thing that the UK needs to really buckle up on, because other countries around the world that are probably less conservative, they're just driving that really hard and really fast, whereas we're a bit stand back. But anyway, thank you for the privilege. A bit of a funky presentation, but there you go.